Entonces vamos a pasar a la siguiente charla de John Klein Consulting, quien nos hablará sobre el mercurio en la industria del cemento. Por favor, John.
Sí, ya. Sí, gracias. Buenas tardes. Lo siento porque tengo mucho para decir. Posiblemente tengo más tiempo ahora, pero no hay mucho tiempo para decirlo. Y entonces voy a hablar en inglés. Espero que puedas seguirme. Voy a hablar con Mercurio. ¿Por qué? Porque es un problema global. Es un problema que existe en el sistema de ecosystem. Sorry, I got to go back to English. And it's a problem for health. Why are we concerned now? Because this group of people, in January of this year, after 4 years of discussion, have concluded on a global mercury treaty. And this group, led by Uruguayan, represented 139 countries and over 95% of the global population and over 95% of the land mass. These 139 countries, including most of the countries in South America, are expected to sign this treaty when it opens up in October in Minamata in Japan. Regulations exist in Latin America today. This information from FISEM, so thank you. Mostly connected to the use of alternative fuels and waste fuels. And all this information is in the slides in the program. In the US, there are 3 new regulations. The first 2, the NESHAP and the SISWI, impacting cement. So the NESHAP is for plants that do not burn secondary materials, alternative fuels, and the SISWI for the plants that do burn alternative fuels. And then a brand new one for the power industry as well. In Europe, they've established for a number of years a best available technology where they seek, here it is, 50 micrograms or 0.5 milligrams per normal cubic meter is their target. Slightly lower than what was shown in LATAM and higher than what the US is going to do. So as I mentioned, mercury is a global concern. You can see concentrated where there is a concentration of both people and industry. Looking specifically at cement emissions, these are the countries rated by emissions in cement. And with a focus on Latin America, you can see not too bad today. Cement as a, mercury emissions as a percent, from cement as a percent of the total, the picture looks a little bit more equal globally. So in the environment, where does the mercury come from? It's available in the Earth's crust at 50 parts per billion. It's concentrated in areas of volcanic activity. Very important west coast of South America. It releases to the atmosphere via volcanic action from natural causes, but it's also released from the burning of fuels and the processing of raw materials in the cement industry and other industries. I think this is a very telling slide, a little bit tough maybe to see. Wyoming is a state northwest, just north of California in the US. And these are mercury samples in a glacier going back, they cored the glacier going back a number of years. And what you can see, the blue spikes are volcanic activity. The gold area here is the gold rush in California. in the late 1840s. So all of the mercury emitted from the gold mining, and then the orange or pink is the mercury from the industrialization, so primarily combustion of fuels. There's three main emissions today. So we have the natural resources. We talked about volcanoes. There are some other natural resources. We have the, I'll come up here first. We have the anthropogenic, the man-made emissions, of which cement is a significant portion. And then there's a fair amount that's re-emitted. So this is either coming from volcanoes or coming from man-made emissions, and then it's deposited in, for example, a forest fire. Fires, other activities will re-emit it. Landslides bring water-soluble mercury back into the ecosystem. So the man-made is roughly 1/3 of the total. And cement is 9%, estimated to be 9% of the global mercury emissions. So we talked about gold mining in California. 37% is from the artisanal gold mining. So artisanal, the very small gold mining operations that use mercury to concentrate and collect the gold. And 24% from power generation, primarily coal combustion. And because cement consumes a portion of the 24%, you can see probably we're slightly more than 9% total. More specifically in cement, it comes in from the raw materials and the fuels. When you look at different raw materials, and this is just one study, you see some very wide variations in the potential mercury content. Big variations, and this is a log scale on the left. I don't know if you can see that in the back. But this is 1 part per billion on the bottom, and that's 1 part per million, 1,000 times higher on the top. And I've been involved with plants that have 2 to 3 parts per million in the raw materials, in the limestone. So this is just one study. And one of the messages for everybody who needs to look at mercury is you need to measure what you have, and you need to measure it repeatedly because it changes. When we look at the fuels, you can see also this is a study that was done in the U.S., different fuels in the U.S. Petcoke, the red line, tires, the blue line, subbituminous coal, that kind of pink line, bituminous coal, the dark blue line, and lignite is the gray line. You can see on average not too much variation, 30 maybe to 100 ppb, parts per billion. But you can see also there's some examples of some extremely high levels. And a lot of cement plants like to use the low grade coal or maybe some of the residuals from coal washing. And since a lot of the mercury is water soluble, you can get a concentration in the coal rejects. So I talked about variability. This is information from one cement plant in Florida that had to report their mercury balance on a monthly basis. So this was coming from a government document, but basically showing the variation in inputs on a monthly basis. And they were fairly steady production. It's more an issue of the change in mercury level in the raw materials. So what we've seen is in different quarries, you can have areas of low and high mercury concentration. As I mentioned, most of the mercury in nature is water soluble. So if you have heavy rains, it can leach out of some areas of the quarry and concentrate in other areas. We've seen plants where it could be concentrated in the fines from the quarry. For different reasons, you can get different concentrations, plus a natural variation. In this one, the HCFA is a high carbon fly ash, which, as you can see here, this power plant may have been doing some experimentation with mercury reduction. So we want to get into mercury cycles, and this is one of the things that makes this so hard to deal with in the cement industry. So it's very similar to like chlorine, if you've looked at a chlorine cycle in a cement plant. Very, very similar cycle. Practically everything boils off in the kiln, gets concentrated back in the other parts of the plant, and then is returned into the system. So if you look at a typical preheater on the right-hand side here, and you look at the raw mill in the bag house, you can see that as the material is either the fuel is fired or the material is heated up in the preheater, almost 100% of the mercury is volatilized off. A lot of that is captured in the raw mill. It depends on the state of the mercury, but the raw mill can capture 90% of the oxidized mercury. Whatever doesn't get caught in the raw mill, some of it gets caught in the bag house on the dust. And if you don't waste dust, then whatever doesn't get caught in these two systems goes up the stack. Also, plants that use the preheater exit gas for cold drying also create a third cycle where there is mercury here concentrated in this duct. This is the area of highest concentration of mercury in a cement plant. You pull that back into your coal mill. Coal's a very good absorber of mercury. So it pulls that in, and that creates a third loop. This is a comparison of the levels of mercury in different, these are 6 different plants. And what you can see here, it's a percent of the inputs. So the raw coal plus the raw feed, these 2 columns, 1 and 3, is the sum of the inputs, 100%. So the kiln feed can be anywhere from 2 times to 9 times, in these 6 cases, 2 to 9 times more mercury because of these cycles than what you've seen in either in your total inputs. You can see a little bit of the fuel pick up some mercury. It depends on how much of your preheater gas is going to your coal mill, if you are using preheater gas. And as I mentioned, the preheater exit is typically the maximum concentration of mercury in the system. Some of that gets caught on the raw mill product. Some of it stays in the CKD, and then eventually, when the system's in balance, all the inputs will eventually go out the stack. But you're rarely in balance because you're either collecting mercury when your raw mill is running or emitting a lot of mercury when your raw mill is down. So this is a collection of data from US plants. I just want to point out these plants on the far right is a whole different scale. So these are micrograms per normal cubic, for dry standard cubic meter, 7% oxygen. I think I heard earlier your measurements are 10% oxygen. It's something to watch for because a lot of countries have different measurement levels. When the raw mill is running is the blue lines, and when the raw mill goes down is the red lines. So what happens is that raw mill, which is a great scrubber when it's running, when you take it out of service, all of a sudden all of that mercury is going towards your dust collector. And these bursts, like I say, they can be 10, 20 times higher in mercury emissions because your dust collector just can't take in that much dust. Usually at the same time your raw mill's going down, your temperature's going up, you may have more or less water spray. So you're doing things in the process that's impacting your emissions. So the state that the mercury is in is important. They call oxidized mercury, basically elemental mercury is anything that's pure mercury. And then I don't know who came up with the term, but they call everything else oxidized mercury. So any mercury compound they consider basically to be oxidized mercury. How much of it, when it burns and when it combusts in the calciner or in the burning zone, you're at a temperature in which you're going to have elemental mercury. As you go through the preheater and through the raw mill, it cools off. It's going to combine with these other chemicals, compounds, and it'll form mercury compounds. And what's good about that, these various mercury compounds are water soluble. They tend to be more sticky in a way that they'll attach to the dust. They're easier to capture in the system. And your elemental mercury is not water soluble, not easy to capture, and rarely becomes particle bound. So in some situations in the U.S., particularly in the power industry, they use oxidizers. They'll put in bromine or halogens specifically to increase the oxidation of the mercury. One of the interesting things is, this is a study also done in the U.S. Long wet kilns tend to be a high percentage of elemental. Long dry kilns, high percent of oxidized. And the preheater is kind of in the middle, preheaters, precalciners. It's kind of interesting, it has to do with the temperature profile in the kilns. And just point that out, that last little piece, every case is unique. There's no such thing as a general rule, so be careful of being caught up in some general rules of thumb. Measurement-wise, I won't spend a lot of time on this. Long dry, long wet kilns, you can use mercury trap systems. They're less expensive, less complicated, but they won't give you spike information. SEMs are expensive to operate, but the modern SEMs will give you both elemental and oxidized mercury. They do need a lot of maintenance to keep going. There are a bunch that have been approved both in the U.S. and in Germany, and you can look on the websites and check out what's available out there. Mercury abatement. There's several ideas being talked about in the industry today. So the easiest, if you can accomplish it, and if you can live with that kind of a reduction, is just to take the dust out of the system. So what a lot of plants are looking at in the U.S. is to take the baghouse dust, put it right into the cement mill in the cement, take the mercury out of the system, break that one cycle. It doesn't have a lot of potential for reduction, but it is an interesting, for a modest amount, it's a very inexpensive way to go. Dust roasting is a little bit of a deviation of that, so you take the dust out, you basically reheat it, take out the mercury, concentrate the mercury, reuse the dust either as raw feed or in your cement mill. A lot of talk about that. I don't know of anybody who's doing that. Chemical fixtures have been talked about, so basically what you try to do is put something into your process that will combine with the elemental mercury, form a water-soluble compound, and either take it out, increase the amount you take out with the dust, or if you have a wet scrubber, you can take it out with a wet scrubber. Nothing has been proven. There's been a lot of talk. Wet scrubbers, which primarily used, I wouldn't suggest it for a cement plant unless you had to put one in for a sulfur problem, but used a lot in the power industry. And you can capture a lot of mercury, a lot of the oxidized mercury in a wet scrubber. Very, very expensive way to go. Dry sorbent injection is by far what's talked about the most, and really activated carbon. So you're putting in a small amount of activated carbon. A lot of them now are brominated activated carbon, so the bromine helps capture the mercury. Much less expensive, but typically you got to take your baghouse dust out of the system. So if you can support the activated carbon in your cement, that's good. Activated carbon has impacts on cement admixtures. So you have to be careful about what you're doing. Air entraining, there's a lot of talk in North America about the impact on air entraining agents, but it'll also impact water reducers, superplasticizers as well. But that is the least expensive, most effective system if you can work it. Semi-dry scrubbing, GSAs, or by various different names. It's very similar to a wet scrubber. You can use multiple sorbents, about half the cost of a wet scrubber. Still a fairly expensive solution, but they are a better solution than a wet scrubber, let's say that. I would say dry sorbent injection is the way to go if you can do that. So just a quick rundown. You can see them all side by side: dust removal, raw material change, wet scrubber, mercury roasting, dry sorbent injection, and dry and wet scrubbing systems. And those are just the numbers again. So I say all this is in the package, so you have that. And this gives you an indication of the cost to operate, including the capitalization. So you can see the least expensive: dust shuttling, dust wasting, dust roasting, activated carbon injection with an existing bag house. Some plants, they can't get enough out with just one bag house, so they'll take the dust out with one, and they'll do the activated carbon in a second bag house. So you might have sorry about that. You might have an ESP followed by a bag house, or a bag house followed by a bag house, with your sorbent being injected between the two. Then, as you can see, the wet scrubber being the most costly. So this year is the year that the Global Mercury Treaty is going to be signed. I think there's over 50 countries in the world, plus the EU, that already have mercury regulations, including quite a few in South America, as we saw. The cement industry is a big emitter, 9%. So this is going to be, if it's not an issue for you today, it will be an issue for you in the future, and probably not too distant future. In preparation, I would suggest to everybody, start to know what your mercury balance, whoops, sorry about that. Start to know what your mercury balance is today. It's not going backwards. So make sure you measure your inputs. And if you see a high variability, keep checking, because you want to understand what's causing that variability and eventually control that variability. From an emission standpoint, you can use traps for long kilns and long wet kilns, long dry kilns, because they tend to have a steady emission profile. If you have preheaters, precalciners with inline raw mills, then you should be using a continuous emission monitor. Steps that could be done, today, tomorrow. You don't have to wait for a regulation. If you know what your high mercury inputs are, look for substitute products, the raw materials or fuels. Remove your bag house if you can. Add it to the cement. If you're using preheater gases for your coal and coke grinding, consider using cooler gases. I know there's a potential safety issue there. You can use the oxidizers also. So that's it. Thank you. I don't know if we have time for questions or...